Hello and welcome back to Math with Mrs. Becker. Today we are looking at calculus and studying a little bit more about derivatives in Chapter 1, Section 7. In many applications, it is convenient to use variables other than x and y. So for example, we may study the function f of t equals t squared instead of using f of x equals x squared. So in this case, the notation for the derivative would use a t rather than an x. So if they're asking for the derivative of d over dt, this just means find the derivative with respect to t. We've been looking at it as d over dx because up until now, when they had us find derivatives, they had the variable as an x. This is just showing you that you can actually use any variable. These two things mean the exact same thing. So let's go ahead and just kind of get used to that notation. So if this is find d over dt, find the derivative, but my variable is a t. The process is the same. This is the power rule. So I would take the 3 out front, keep the t, reduce the exponent by 1. You're done. That's the same thing. Okay, this is the sum rule. Because I have more than one term, you just find each derivative separately. But this is telling me find the derivative. My variable is a t. So the 2 comes out front. 2 times 2 is 4. I still have a t, reduce the exponent by 1, so it's just 1t. Plus, this is a linear term, 3t. When you are finding the derivative of a linear term, it's always going to just be the slope if you're looking at a linear function, or in this case, just a 3. Recall, if y is a function of x, we say y equals f of x. This is just reminding you that these are interchangeable. Y is the same thing as f of x. So in this case, it's common to see dy over dx. Find the derivative of y with respect to x because x is the variable, y is the function. Okay. Other times, remember, another way that you can see a derivative is they put that little apostrophe symbol in there. That means that you are finding the derivative of the function, again, with respect to x. Okay, so the way that you read it is labeled right here for you, the derivative of y with respect to x. If v is a function of t, it would be read the derivative of v with respect to t, and it would be written like this. Whatever your variable is, that is what is shown on the bottom of that notation. So for example, if v equals 4t squared, the derivative of v with respect to t, 2 times 4 is 8. I still have the t, reduce the exponent by 1, so it goes from an exponent of 2 to just 1. Okay, same thing here. Now here are those rules that we looked at in 1.6. Remember, we had the constant multiple rule, we had the sum rule, and we had the general power rule. We are finding the derivative of s with respect to p. P is our variable. I'm going to take the 3 out front. Remember, that's that constant multiple rule. I don't want to deal with it right now. I'm going to move the 3 up front. Then I'm finding the derivative with respect to p of p squared plus 5p plus 1 to the power of 10. This is the general power rule because I have an exponent over a full group. The 3 is still there. When I find the derivative, remember, you take the exponent out front. Keep the function the same. Reduce the exponent by 1. Now we multiply by the derivative of whatever was on the inside of the parentheses. The derivative of p squared is 2p, plus the derivative of 5p is 5. So this is what I have so far. We have to simplify this. I can just go ahead and take the 3 times 10, and I'm totally good if you leave it as 30 times p squared plus 5p plus 1 to the power of 9 times the group 2p plus 5. If you keep it like that, you're golden. I know on the back of the book, sometimes what they'll do, because this has an exponent of 1 and this is just a single term, they will go ahead and distribute that and show it as 60p plus 150. Then I have my p squared plus 5p plus 1 to the power of 9. These two things are equivalent to one another. One is not better than the other, but it's important for you to know that if you have this and you check the back of the book to see how you're doing and it shows like this, I want you to know how they got that. And for you to realize that, hey, you had the same thing, this is okay. Or maybe you did this And the book kept it like this. It's just important for you to realize that they are equivalent and how you can get from one form to the other. Okay. Now this one's a little bit trickier. So this is kind of like an intro to calculus 2 because we have multivariables. We have A's, T's, S's, all those things. So if you're trying to find a derivative, it's important to look at the notation. This is saying find the derivative if your variable is a t. That means A is a constant. S is a constant. What that means is it's a number. Our variable is t. So I take the exponent from the variable and multiply it out front. So it'd be 2a. The t stays, reduce the exponent by 1. Now here's the next piece. -1, multiply it out front. So it's negative s, because -1 times s is negative s. I still have the t, reduce the exponent by 1, so it's a -2. Now s is not a variable. This is a constant, meaning it's a number. The derivative of a constant is 0. From here, this is your answer at this point, but remember you cannot have a negative exponent in your final answer. So we go ahead and say 2at minus s over t squared. Okay, so whatever this variable is right there, that is your variable that you're finding the derivative. Find the derivative with respect to t. Now guess what? We can actually find what's called a second derivative. And what we do is you find the first derivative, then you find the derivative of the first derivative. So you have your original function. When you find the derivative, here's the notation. Then if you find a second derivative, there's the notation. So let's go ahead and do this. So I'm going to simplify this. This means 1 over x. So this is x cubed plus, if I have 1 over x, that's the same thing as x to the negative first power. And that's how I'm going to write that. So that is our original function. Our first derivative, this would be 3x squared minus 1x to the negative power of 2. Now, typically, I would go ahead and rewrite this as a fraction, but we're not done. This is like our middle step. We want to find the second derivative. So now I find the derivative of the first derivative. 2 times 3, oh, I got to get my notation here. 2 times 3 is 6. I still have an x. I reduce the exponent by 1. -2 times -1 is a positive 2. I still have the x. Reduce the exponent by 1. So your second derivative is 6x plus 2 over x cubed. You just found a second derivative. Okay, let's go ahead and find a second derivative here. So my first derivative, this is a linear function. Remember, when it's a linear function, your derivative is the slope. So it's a 2. Your second derivative, if I take the derivative of just a number, the derivative of a constant is 0. Okay, let's look at the next one. Now this is f of t. Notice the notation. This is a t because my variable is a t. So my first derivative with respect to t is 1/2. Oh, I put a t there. 1/2 t to the negative 1/2. Bring this out front, minus 1/2 t. Remember, if I am minusing 1 from negative 1/2, that's the same as subtracting a 2 over 2. So this is negative 3/2. That's the first derivative. Now I'm leaving it like this because that's not my final answer. Yes, I understand I have negative exponents and I have lots of things going on. But let's go ahead and find that second derivative before we simplify it. Negative 1/2 times 1/2. Remember, when you're multiplying fractions, it's top times top, bottom times bottom. So this is negative 1/4. T, if I subtract 1 from the exponent, it's negative 3/2. Now here, I had negative 1/2. I have to multiply that exponent up front. Negative times a negative is a positive. 1 times 3 is 3. 2 times 2 is 4. I have a t. Now I need to go ahead and subtract 1, which is the same as subtracting 2 over 2. So this is negative 5/2. Now if I go ahead and write this using rational, or I'm taking my rational exponents and writing them as radicals, this t is on the bottom. It's a square root of t cubed plus 3/4. This is on the bottom. It is a square root of t to the power of 5. So what I need to do, these are square roots, so I need to have an even number so I can cancel that out. So here, if I multiply top and bottom by the square root of t, this would be negative square root of t over. Now here I technically have 4 t's, so the square root of t to the power of 4 would be t squared. Plus, here I have 5. I need an even amount, so I need one more. So if I multiply top and bottom by the square root of t, this would be 3 times the square root of t. This would be 4. Go ahead and look at this. So this would be 4 out front. 5 and 1 more would be 6. The square root of t to the power of 6 would be t cubed. And I'm going to go ahead and let you leave it like this. We could go crazy and wild and go one more step and try to do common denominators, but you do not have to do that, okay? Because if I look, here's the derivative of this term. This is that sum rule. So I do not need to combine them because the derivative, the second derivative of the first piece would be negative square root of t over t squared. The second derivative of the second piece would be 3 square roots of t over 4t cubed. Okay, so don't worry about trying to make a common denominator. We didn't have to do it there. We didn't have to do it there. Okay, let's go ahead and keep looking. Unfortunately, the process of differentiation does not have a standardized notation. So what happened is mathematicians, they kept inventing new ways to do derivatives or working on it, and they kind of, they all kind of had their own little notation. So there's not a standard notation, meaning it's important that you're familiar with the terminology and the way that they say this. This is a derivative. This is a derivative. Here's a way to say a derivative. Here's the way to say a derivative. So all 4 of these things, if you see any 4 of those notations, it means the same thing. Find the derivative. Now that we have a second derivative, here are the notations that you're going to see that indicate, hey, don't only find the derivative once, find it twice. So you'll notice here it's 2 of those little apostrophe or prime symbols on both of those. You'll notice the powers of 2 there. It's just telling you, go ahead and find the second derivative, okay? So here's another notation. This means, notice that it's our second derivative. Find the second derivative, then replace the x with a 3. So you guys, it's getting so fun. So here's the original function. Go ahead and find the first derivative. So 4x cubed, 3 times negative 5 is negative 15x squared. That's a constant, so the derivative is 0. Find the second derivative, and I know it's a second derivative because of the notation. 4 times 3 is 12x squared. 2 times negative 15 is negative 30. I had 2 x's. I take 1 away, because remember, you always reduce your exponent by 1. So this is my second derivative. So this means find your first derivative. Now, replace your x's with a 3. So 12 times 3 squared minus 30 times 3. That's what that notation means. So fun. 12 times, there's only 2. 12 times 3 squared minus 30 times 3 is 18. So here are your 2 answers. Second derivative, what's the value if you sub in a 3? Okay. Now here's another one. Again, we're kind of looking at that. No, I guess this one does only have the one derivative or the one variable. I thought I gave you another sample of CALC 2. CALC 2 is where you're going to see multivariables. This one we're good. So find the derivative of s with respect to t. So this is find the first derivative, fill in a negative 2. So the first derivative, 3t squared, 2 times negative 2 is negative 4t plus 3. Now, you take the first derivative and fill in a negative 2. That's what this is. So we found the first solution. Now it's 3 times negative 2 squared minus 4 times negative 2 plus 3. 3 times negative 2 squared minus 4 times negative 2 plus 3. It's 23. Now they want us to find the second derivative. So I take the first derivative and differentiate that. 2 times 3 is 6. We still have a t. This is a linear term, so it's going to be negative 4. The derivative of the constant is 0. There's the second derivative. Now, take the second derivative and fill in a negative 2. So 6 times negative 2 minus 4. 6 times negative 2 is negative 12. Negative 12 minus 4 more is a negative 16. Okay, let's go ahead and look at just a little real life scenario, okay? If C of X is a cost function, so remember it's how much something costs, then the marginal cost, remember we talked about marginal cost as being the first derivative? The marginal cost meaning how much more would it be to increase the current production level up one more unit? The marginal cost of producing A units, then you go ahead and fill that in. So it's approximately equal to, if you take the original function, the number of units you're making plus 1, go ahead and calculate that, minus, take your original cost function, put in how many units you're creating right now, okay? It is the additional cost that is incurred when the production level is increased by 1 unit. That's the definition of marginal cost, okay? Suppose that the cost of producing X items is that bad boy, and the daily production is 50 items. What is the extra cost of increasing daily production from 50 to 51? So we're currently making 50 units. So go ahead and fill in a 50 for there. So 0.005 times 50 to the power of 3 minus 0.5 times 50 squared plus 28 times 50 plus 300. Okay, so the cost when you're making 50 is $1,075. They're like, okay, but now we're going to go ahead and make 51 items. Well, if you were really careful when you entered this into the calculator, you can go ahead and up arrow and change all of the 50s to 51. And that's what I'm going to do here, 51. Okay, so the cost of making 51 units is $1,090, and it's 0.755. Remember, we're talking about money, so we have to make sure we round it to the hundredth, so 0.76, okay? So go ahead and find out what is the extra cost. So we subtract. So $1,090.76 minus $1,075. The extra cost is $1,576. Now they want us to find the marginal cost if X is 50. They're saying rather than doing all of this work like we just did, we could go ahead and find the derivative and fill in the current number of units that you're creating. So if I find the derivative, 0.005 times 3, okay, because I'm taking the 3 right here. So I'm finding the derivative. It's 0.015x, reduce the exponent by 1, so it's a 2. 2 times negative 0.5 is going to be a negative 1. It's just an x. Okay, so if I have 2 times negative 1/2, it's going to be a negative 1. I had 2 x's, reduce it down to 1. The derivative of 28x is just 28. So that is our derivative. Now to find the marginal cost, if x is 50, we go ahead and fill in a 50. And if I go ahead and calculate that, 0.015 times 50 squared minus 50 plus 28. It says that it's $15.50. So what they want you to realize is that this is a really good way to make a prediction. Okay, when we're talking about this much money, we are pretty darn close when we do that calculation. So rather than having to find your actual cost right now, how much would your actual cost be? Go ahead and subtract them because this is a lot more work. A quicker way to make a prediction, meaning it's not going to be exact, but it's going to be pretty darn close. Go ahead and find the derivative, fill in your current level of production, and it's a pretty good idea of how much the cost would increase. This works for marginal revenue and marginal profit as well. When you talk about marginal revenue, go ahead and find the derivative of the revenue function. If you want marginal profit, how much more profit would you make if you produce and sell one more item? Go ahead and find the first derivative and then fill in what your current production level is. Hope you guys had a great time talking about derivatives. Here is the suggested assignment out of your book, and I'll talk to you soon. Bye.